I'd now like to take this model of a spring and take it in a different direction here, where we eventually bring in the coefficient of resistance, and which is going to make our differential equation just a little more complicated, but it also makes it more realistic. And so, going back to where we started with all this, we formulated a differential equation by looking at the overall force on the spring system. Mass times acceleration is force, is the force being pulled down, that's mass times gravity, or weight, minus k times L plus y. Now, we had determined that according to Hooke's law, the force exerted on the spring stretches it a length that is proportional to the amount of force. And so, in other words, the length stretched by the weight is proportional to the length being stretched. Hooke's law. And k is the constant of proportionality. And by the way, I don't think I mentioned this before, k is known as the spring constant. So it's a constant that gives a measure of the stiffness of the spring. So for example, if the weight is constant and a spring is stretched out a long ways, then k is going to be rather small in order to compensate. However, if a spring is very stiff, like a car shock absorber, it doesn't stretch much at all, very little stretch, and so the L is very small. K has to be much larger in order to equal out to this force. You know, if this force is the same on two different springs, then a stiff spring will stretch very little, will have a large spring constant. A very loose spring will be the other way around. It'll stretch a long distance, but in order to equal this constant, k will be actually very small. So anyway, that's what k is really telling us. And it's known as the spring constant. Okay, well, let's first of all play with this equation, and it's my double prime equals to mg minus kl minus ky. And because of the Hooke's law relationship here, mg equals to kl, when they're subtracted, they cancel one another. And so we had come up with this equation, my double prime plus, put this on the other side, spring constant times y equals to 0. Alright, now for a reason that will become apparent in a moment, I want to rename k as mass times omega squared. So I'm going to let k equal to m omega squared. This gives us my double prime plus m omega squared y equals to 0. Now that turns out to be very convenient for us. For one thing, we can divide mass out. Y double prime plus omega squared y equals to 0. And what are the units of omega? Well, in this equation, y double prime is an acceleration unit. And so acceleration is always the distance per time squared. For example, feet per second squared or meters per hour squared. Those are acceleration units. And over here I have omega squared times a distance, y. And so when we cancel here, omega squared is 1 over time squared. So the units of omega are 1 over time. Well, 1 over time is actually a frequency unit. Frequency. And so now we think in terms of frequency, we think of like cycles per second, or revolutions per second, or vibrations per second, something per second, And if it's per second, then those are hertz. Hertz units represent frequency. And so that's what omega gives us. And if you've taken some trigonometry very recently, you'll perhaps have encountered this idea in graphing trigonometric functions, sine and cosine waves. I teach that all the time, so that's why it's right around the top of my head. All right, so here we have this formulation here, which is kind of nice. All right, well, so from now on, rather than call this side G over L or something like that, which I believe it was. I think K was equal to, if we divide the M out, it was G over L. Yeah, it was in one of the previous videos. Let's look at it in terms of frequency. And now I want to ask, well, how do we build in a resistance? Because when we solve this problem right here, we're creating a sine or cosine function. In fact, let me just go ahead and do that real quick. When we solve this, the characteristic equation is m squared plus omega squared equals to 0. So m is equal to plus or minus I omega, because omega squared goes to the right side as negative omega squared. We take the square root of that negative, and then that introduces the imaginary unit I. And so my solution would probably be written as y equals to c cosine parentheses omega t plus delta, or as y equals to c sine omega t plus delta. Okay, and by the way, I think that there may be a difference in plus minus signs if your deltas are the same, and so if you consider these deltas to be different depending upon the formulation, then you can write them both as plus deltas. Delta, again, is a phase shift. It just translates the graph left to right. That's what it does. But omega t is what? If omega has the units of 1 over time, and if I multiply by time, the time cancels. And I get literally angle. And so actually omega t would represent an angle. And okay. And here's our phase angle. Omega t is an angle. And instead of calling it theta, by writing it as omega t, we've introduced the possibility of tracking the motion, because now we have the time variable involved, the time parameter. All right. Some things to chew over about all this, how this all fits together. Well then, what are we going to do with this? Let me do some erasing and I'll introduce the coefficient of resistance. Before I do all the erasing, I want to just finish my thought here a minute ago. The claim was that this model here results in simple harmonic motion. Simple harmonic motion is described by either a sine wave or a cosine wave. And the solution was a sine or a cosine wave. So that's what's meant by simple harmonic motion. And such a spring would never come to rest. It would just oscillate forever. And so, as you can tell, that's not terribly realistic, because there has to be some element there that's going to bring that spring to a rest. Otherwise, you have perpetual motion. And the spring is vibrating. It creates a tiny bit of heat inside. It may be interacting with the surrounding air or liquid or whatever it's immersed in, if it's not in a vacuum. And so all those little factors are resistance quantities. And so how do we fit resistance into this? Well, here's a good way to do it. So, but I am going to, I think, erase the rest of this before I do that. I've gone back to this equation, which was our simple harmonic motion before dividing mass out. And to that, I'm going to add a first derivative term. And it's done in kind of a, looks like it might be kind of an unusual way. I have my double prime plus 2mr y prime plus m omega squared y equals to 0. And so this term here is the coefficient, I'm sorry, it's the resistance factor. And the resistance is proportional to velocity. So the faster it springs back, the resistance is proportional to that. So if a spring is springing back twice as fast, there's twice as much resistance. Does that make sense? Is that the way it should be done? Well, it seems to be a reasonable assumption. I think when we build these models in physics, we don't always take into account every single little nuance. And maybe you study that as a physics major, and when you get to the upper division or grad school, maybe you look into everything that you can possibly think of. But here, it's a good, serviceable working model, and gives us good answers. So, reasonable to assume that resistance is proportional to velocity. Okay, now then, so 2m, the way our book terms it, I don't know, this book was written in 1963. I don't know if these terms are generally acceptable, but 2mr, according to this book, this is called the coefficient of resistance. Coefficient of resistance. There we go. So that's what that is. I haven't always called it that when I'm teaching, but I thought I will be a little more formal this time and at least do what this book does. And I assume these authors, I think it's safe to assume they know a lot about this than I do. So, about this terminology. All right, well, if we introduce this coefficient of resistance into the problem, and I'm sure it was put in order to, so we can cancel out m, then here's our basic equation. Y double prime plus 2r y prime plus omega squared y equals to 0. And it's kind of a nice tidy equation, and it's second order, linear, homogeneous, and guess what? We have constant coefficients. Omega and r are constants. So what would be the units, by the way, of the coefficient of resistance? Well, let's get the units of r first. So I have acceleration units, which is, what was that? It's length or distance per time squared. And this has to be distance per time squared. See, these units have to be the same across the equation because we can't add things with different units. Have I made that point before? If I add 10 feet plus 13 seconds, I don't get anything that makes sense, do I? Because the units are different. And we can only add things that have the same units together. It's the same as combining like terms in algebra. And so each of these is an acceleration unit, and before I divided mass out, it was actually each of these was a force unit. Divided mass out turned into acceleration. So the r, y prime, well, y prime is distance per time times letter r, 2r if you want, but it doesn't matter, times r is equal to acceleration unit, distance per time squared. So what is r? And you can see that r, the units of r are frequency units, 1 over time. And so I may express it r, or your book may express r in terms of hertz, which are frequency units, because we need 1 over time in order to make this to work. So anyway, the coefficient of the 2mr, the coefficient of resistance then, the units for it are mass per time. So that's the coefficient of resistance is mass per unit time. And R itself is just frequency, 1 over time. All right, I think it's very good to look at units and get all that kind of squared away. So here we have a second order linear differential equation with constant coefficients, homogeneous, and so our typical method of doing this is by looking at the characteristic equation. And the solution to the complementary solution is the solution to the differential equation. And so our characteristic equation is m squared plus 2rm plus omega squared equals to 0. So in a minute you're going to see why the 2 shows up. It really is for our convenience. And now I'm going to solve that by using the quadratic equation. So m is equal to minus this coefficient, minus 2r, plus or minus the square root, this coefficient gets squared, 2r quantity squared, minus 4 times 1 times omega squared, and all that's divided by 2 times 1. There we go. So let's see, we have minus 2 plus or minus square root of 4r squared minus 4 omega squared over 2. And here we can factor out a square root of 4. And square root of 4 is 2, isn't it? Minus 2 plus or minus 2 square roots of r squared minus omega squared divided by 2. At this point we can divide the 2's off. And so the root of my characteristic equation is m equals to, and I forgot something, there's an r right here. Better put that back in, you probably saw it. Make sure that r is there. Divide by 2, m equals to minus r plus or minus the square root of r squared minus omega squared. There we go. So, let's write out the answer. So here we are, the complementary solution, which is the full solution. Y is a function of time, y is a function of t, is equal to a constant times e to each root. So at C1, e to the first root I'll write as minus r, not plus or minus, but just plus, minus r plus square root r squared minus omega squared, and times t. That's why I forgot to write t. I was shooting this earlier and I didn't realize it till way too late. And then plus another constant, c2 times e to the minus r minus the square root of r squared minus omega squared, all multiplying t. Alright, now we can work with that a little bit. Each of these has an e to the minus rt in it. And so I can factor that out because, rules of exponents means I can split up this addition or that subtraction into a product, and each product contains an e to the minus rt. So this is going to be e to the minus rt times c1 e to the square root r squared minus omega squared times t plus c2 times e to the negative square root r squared minus omega squared times t. There we go. So that's kind of our basic solution, and you can see why the 2 was put in there, because the 2 we were able to conveniently factor out a constant, and so we have this these square roots without a fraction in it. Okay, now we have a couple things to look at here, and what happens when r squared minus omega squared is positive. That's our first case. And if it's positive, that means the square root is a real number. What happens when r and omega happen to be equal? In that case, that's 0. And so I would just have e to the minus rt times c1 plus c2. That's an interesting case. And then finally, what happens when this is more interesting, I think, when r squared minus omega squared is negative, that means these are imaginary numbers. Being imaginary, we're going to end up putting this in terms of sine or cosine and getting a harmonic motion, except this part here will dampen it. So I'm going to, I think, leave this here, and let's look at the three cases. Up to this point, we've taken this equation and solved it and got this mess. And we want to look at three separate cases here. So the first case, call it case 1. What happens when r squared is greater than omega squared? Well, when it is, then the square root is the square root of a positive number, isn't it? And so, but here's something I think pretty interesting to consider. The square root of r squared minus omega squared is less than the square root of r squared. Isn't that true? Omega squared is a positive number. We subtract a positive number from r squared. R squared is still larger, so we still get a positive number, but it's got to be smaller than just r squared without subtracting that number. And the square root of r squared is equal to r. So what that tells us is that when you multiply e to the minus rt times c1 e to the square root r squared minus omega squared t, then I'm kind of going backwards here. If I re-add these exponents, e to the minus rt plus the square root r squared minus omega squared t, factor the t out if you like. Minus r is going to be a larger negative number than r squared, square root of r squared minus omega. So, is that true? If I had minus r plus the square root of r squared minus omega squared, and is that actually negative? Well, if I add r to both sides, square root of r squared minus omega squared is less than positive r. So I could go from here, subtract negative r, and it's going to be less than 0. So in other words, this whole part is a negative coefficient multiplying time, t, which means as t goes to infinity, this portion goes to 0 as t goes to infinity. Again, it's because this, if you factor t out here, this whole coefficient of t is negative, so as t goes to infinity, you have e to a very large negative number that goes to 0. So this, as t goes to infinity, this term vanishes. Is that the same over here? Well, even more so, because if you went back and again re-added these terms, re-multiplied these together and re-added these, you'd have minus RT and then minus the square root. They're both negative, so that's obviously, you're adding two negatives together to get a negative times time. When time goes to infinity, you have e to a negative number getting very large negative. That also goes to 0. So in other words, in case 1, what I've just argued or observed is that as time goes to infinity, then y goes to 0. In other words, the limit as t goes to infinity of y at t is equal to 0. Well, what does that mean? That means the spring stops bouncing. That's all it means. The spring comes to a rest. And All right. Well, matter of fact, that's it's considered. It's called over damped. The over damped, D-A-M-P-E-D. The over damped situation is when r squared is greater than omega squared, and it comes to a rest. Now, the graph in terms of time will look like this. If it's asymptotic, goes to 0. And so this is the over damped case, time, and y is displacement, how far it bounces. All right, so over damped is good. Now it could possibly do some funny things. I'm kind of looking in the book that I've been teaching out of, and one of the graphs they show is they have a couple of graphs. It could go like depending on what these numbers exactly are. It might be like this. It could be like that. It could just go up a little bit, drop down. It might be something like this. Okay, so it might actually swing too far and then come back. And so it really depends upon what all those numbers are. You could get some little bit different graphs. But in all cases, it's asymptotically approaching 0. And that's over damped. Alrighty, so you might get one bounce out of it. I don't know, depending on what the numbers are. So that's case 1, over damped. And what is over damped in real life? Well, your shock absorbers tend to be over damped. For example, because if they're tight enough, then the stiffness and actually the resistance is enough to overcome any kind of bounce. And so when your car hits a bump, it bounces and then comes to a rest, so you don't get this up and down motion. Now when your shocks are busted, then your car might bounce up and down. And so the idea is that the springs are good enough that they're over damped, and so that you don't get a bounce. There you go. So that's the situation of over damped. All right, now let's look at case 2. Our second case is perhaps a little more hypothetical than realistic. It's when r squared is actually equal to omega squared. When it's tuned like that, we call that critically damped. And so that means that these square roots are 0. So our solution, y at t, would be e to the minus rt parentheses c1 e to the 0 plus c2 e to the 0. Well, that's c1 plus c2. Adding two constants, we get a single constant, ce to the minus rt. Well, this is a classic exponential decay. And so exponential decays work like this. There's no wiggles or bumps or anything into it. They just smoothly decay like so. They're also asymptotic. As t goes to infinity, the spring comes to a rest, but it doesn't have a chance, as we saw sometimes in the overdamped case. It's possible it can go underneath and come back. It doesn't have a chance to really stop. in theory, it goes on forever before it truly comes to rest. So, for example, if you have a screen door or some kind of door with a hydraulic hinge on it or a spring hinge on it, the goal is to tune those to be critically damped as best as possible. And that way the door comes to shut rather smoothly, but doesn't slam. Okay, if it was underdamped, then it would want to, if the door jamb wasn't there, the door would want to come back and bounce. So the door would slam because it's trying to go farther. If it's over-damped, which probably most doors are anyway, it does still come to a rest. Maybe a little quicker. Maybe a little quicker it comes to a rest. Critically damped very smoothly comes to a rest when the door closes. So that's the idea of critically damped. Like I say, it's kind of hypothetical because how could you make something that's truly critically damped? You could get close to it, I'm sure. So anyway, the critically damped situation is just a single constant, and it's an exponential decay. So to me, the most interesting one is the underdamped vibration, and that's when the spring continues to bounce but eventually comes to a rest. And so let's take a look at that. We've come to what I think is the most interesting case, the underdamped case. This is where r squared is less than omega squared. So if that's less than, that means that r squared minus omega squared is negative. And so in a sense we should write the solution this way. Y at t is equal to e to the minus rt, parentheses, c1, e to the I times the square root of omega squared minus r squared. Notice I reverse these, times t, plus c2 e to the minus I square root omega squared minus r squared times t. So this was negative. By reversing it, this becomes positive, but I had to factor out the square root of -1, which is I. So we get the case where this is kind of a plus or minus, complex number situation. Well, as we've seen before, we can write this in 3 other ways. One involving both sine and cosine together, or we could write it as what? E to minus RT times the cosine of square root omega squared minus r squared t plus delta, or as e to the minus rt sine parentheses square root omega squared minus r squared t plus delta. Okay, well, so what's going on? What does it look like? I got to do some erasing here. So it might take a minute to write this down for your notes. Shut off the video if you need to, because I do need to erase, and I want to draw a graph of what this looks like. There's probably a name for this graph. I'm kind of, if I knew it, I've lost it. But it's the underdamped harmonic oscillation situation. And we have basically either a sine or a cosine wave jumping up and down, but the amplitudes are constantly decreasing. And so the spring does come to rest as t goes to infinity. So it starts bouncing and bouncing and finally just quivers and comes to visually a rest. Theoretically, it'll still vibrate forever, but in reality that's probably not true. But in any event, mathematically that's what it says should happen. Now the amplitudes follow an exponential decay, so that almost looks linear, but I meant it to look exponential, with a little curve. So the e to the minus rt, and here negative e to the minus rt, sort of forms a boundary to this oscillation. And so it jumps up and down in between these two exponential curves. And let me see if I can draw a little better representation here. There's an exponential curve. Here's the reflection. And so the oscillations fit in between there. So actually, I'm told that if you discharge a capacitor, the voltage coming from it will, AC of course, alternating current voltage will oscillate like this. and a discharge from capacitor. So this shows up in not just in physical springs, oscillations, it shows up in electronics. And matter of fact, AC current, in a sense, is an oscillation between positive and negative charges. And so this mathematics tends to work pretty well in studying AC current, at least the complex numbers and so forth enter into it. So we do calculations in real life with complex numbers, and not just with springs, but with electronics, alternating current, my understanding. Anyway, that's what the underdamped situation is. So it could be a sine or a cosine here. Okay, well, we've kind of laid out what can happen with this differential equation, which is the equation involving resistance, damped vibration, and is it overdamped, critically damped, underdamped? But damped vibration is this. Now, I haven't put anything on the right side. It's called a driver function when we have a function on the right side. Well, we'll leave that for later. Let's work a problem or two with this first.